Today I'm going to be talking about extremely elastic elastomers, and yeah, I had to do that just to be silly. Primarily looking at two materials, the first of which is going to be silicone, and that's a pneumatically actuated silicone soft robot. I showed a video of it a few weeks ago earlier in the class. And the second one's going to be the FDM filament called Ninjaflex, which is a flexible filament usable on most consumers type FDM 3D printers. So silicone has some pretty awesome properties overall. It's extremely water repellent, has very low thermal conductivity, very high thermal stability. You can bring it up to pretty ridiculous temperatures and it doesn't really care. You can tune its electrical properties from completely non-conductive to fairly highly conductive. It's fairly resistant to most chemicals as well as oxygen, ozone, and UV, so it's good for outdoor applications. Standard places you'll see it, silicone caulking around windows and around seals. Oven mitts are often have either a silicone coating or they're made of silicone. And then the last one there is one of the little soft robots. It's a little pneumatic gripper picking up an orange. Material properties, this is just handbook properties for the silicone that we're using in the printer that we're building, which is the Smooth-On EcoFlex. It's got pretty huge elongation. Their softest set is 1,000% elongation at break, so crazy elongation, and it's actually still gives you some decent properties. It's a fairly strong. It's kind of interesting to play with the stuff, but obviously this is not a material that's been used yet in additive manufacturing. It's one that we're currently building a printer to print. Smooth-On's one of the main manufacturers of silicone materials, and they have a huge range. Everything from this stuff, which is usually used for mold making, also used for soft robots a lot. It's used extensively in the special effects industry for masks and makeup, and they do it for crash test dummies. They actually make a few different mixes that are used as ballistics gel. So they have a huge range of different materials, and it's really tunable. There's a lot of different additives you can put into it that completely change how it behaves. Some of them make it cure really fast. Some of them there's a couple additives that'll give you up to a 24-hour curing time, and some of them will bring that time down to closer to around 30 seconds. So we're trying to get it to the mix where we can push it through the extruder and not have it solidify inside the printer. Also, coloring. There you can mix basically any mix of colors, and it's pretty simple to work with. It makes a lot of a mess, but it's pretty simple to work with and fairly biocompatible, so you don't really need to worry too much about toxicity. So one of the main uses that I'm interested in with this material is soft sensors, and this is one that the reason that we're building this printer for my senior project is these, because they're incredibly difficult to make right now. They take either a 3D printed or machined mold that you then have to mix and fill with silicone. But when Dr. Manguch showed us how to mix them, he also showed us how to use a needle to pull the bubbles out of it so that you don't get stuck bubbles in it. And then you have to vacuum chamber to get all the extra air that's inside the silicone out, and then curing and post-curing, and then in the case of these, injecting a indium gallium alloy into it, which can be used to turn one of these little sensors into a variable resistor. And so for what we're doing, we're going to have a printer that can print this entire part with the microchannels already in it. And then you just put in the alloy and you're good to go. So we're hoping to make it a much faster process. Instead of about a 4 to 5 day process, we're looking at a 1 day process. The indium gallium alloy is liquid at room temperature. It's a liquid, and you fill these little microchannels, and you can actually see them. You can't see them too well, but this little block here, it's not actually a flat block. It's a squiggly microchannel that goes back and forth a lot of times. And then as you stretch that sensor, the channels become smaller in diameter, which increases the resistance, and overall you end up with more resistance across the whole sensor. So you can actually use these little things to measure how far you've stretched the little tiny silicone sensor. And they also work really well for force sensing. You can have one of these, like a small grid with a lot of pillars in the center that's full of the indium gallium alloy. And then if you press on it, it pushes the material out to the outside, so resistance across the whole part drops. And you can do a lot of tuning for the different properties you want. But right now, it's really hard to make these accurately, and it's hard to make them quickly. So we're trying to improve that a lot, and it's a place where 3D printing should hopefully, fingers crossed, if everything works right, come through and make a much easier to use process. That's not supposed to be there. Okay. So the next, material here is looking at Ninjaflex, which is they're calling a thermoplastic elastomer. It's just PLA with some additives in it. This is what I found for their comparative properties with other materials. They are kind of silly. The 1 is worst, 2 is better, 3 is best. That is their scale of comparing. That's like, I was able to find good durometers, but for the actual tensile strength and stuff, they won't actually give you the data, and I haven't been able to find it online. So it's one of those, if you want to know it, I guess you take something and you break it. So it's a little bit weird. Their entire website has a very do-it-yourselfy feel to it, which it's made for the do-it-yourself market. And there are some case studies. I will preface this with I hesitate to really call these case studies because they're more like little news blurbs, but there are some pretty interesting demonstrations of what this material can do. They make mountain bikes, and so they printed mountain bike grip handles directly off a 3D printer. They were able to use them. They're really flexible and really springy. They also did some printing of tires for RC cars, and it was really, they found that it worked really well, and it was a lot cheaper than the traditional methods that they'd found. They said it was about $4 for one of the handles, where at their bike shop they were selling them for $10. So, hey, that's a good use of it in my opinion. It's where it actually is cheaper. So, the next one, these guys actually have a pretty cool video of some different materials that have been made with it. So they use Lulzbot is a company that makes one of the better rated 3D printers. One of these was a video. So, and then Adafruit has some demos of some of their prints. This is one where they made a bumper case for a cell phone, and that way you can customize parts. This is more on the do-it-yourself or cool gadget making, but also distributed manufacturing. It's a kind of interesting idea where 3D printing can bring a lot to the game, because a person can design the case they want for their phone, and if you go onto a lot of the part sharing websites, people have made the templates for these for basically every phone in existence, and you can just press print and have a case that has little things on it that you like, and that has patterns you want. The other kind of cool stuff they did, they made these flexible spikes out of a clear Ninjaflex that have lights underneath them to make them look cool. So there's some pretty interesting stuff that you can do, and it's actually usable on a standard FDM printer. So I'd love to have more material data on it, but they don't really give you material data. So, and this is also, I will say, a material that is not used in non-FDM applications. Ninjaflex was specifically formulated for use in FDM and use in 3D printing, so it doesn't really have non-FDM properties, because that's the only time it's ever used. So that's it.